Welcome to a session on deviation of real gases from ideal behavior. In this session, we will be seeing deviations observed in the plots of PV isotherms of real gases, compressibility factor and Boyle's law, Charles' law, Avogadro's law. These three are gas laws, and these are the conditions at which the deviations are occurring. We will consider the two conditions, that is high temperature and low pressure, which is the first case. When temperature is very high and the pressure of the gas is very low. In these two cases favor the volume to be very high. Now, when volume is very high, we know that the gases, they move apart and there will not be any appreciable intermolecular attraction between the gases. That is one case. The other case is when the molecules are far apart, they occupy a very large volume, and when the volume is very large, the volume of the molecules, that is the volume required by the molecules or the volume occupied the molecules, are negligible. Okay. Now, the reverse condition is temperature is low and pressure is high, which favors a very low volume of the gas. When at low temperature and high pressure, temperature is low but the pressure is very high. Now, the gas molecules come together because the volume is very small. Okay. Now, in this condition, when the gas molecules are brought closer together, there will be intermolecular forces of attraction existing between them, that is for sure. Okay. Again, the volume has been decreased to very small volume, and in that volume, the volume occupied by the molecules will not be negligible. So, keep this in mind and let us see how does this being experimentally proved. The first one is, we are going to plot PV against P. Isotherms means the temperatures are kept constant. The temperature is given, that is T is equal to 273 Kelvin. Okay, that is 0 degree Celsius. You can see that is for the gases nitrogen, carbon dioxide, hydrogen and helium. You can see there are two types of graphs, that is one set, that is they keep on increasing as pressure increases, that is the value of P into V, product of P into V, while in two other gases, that is for nitrogen and carbon dioxide, you can see that it first decreases and then keeps on increasing. Both the decrease for carbon dioxide is a greater one, and for an ideal gas, we know that PV is equal to RT, or you can say that the product of PV should be a constant if temperature is constant. There is no variable, because when T is constant, R should automatically, we know that it is a constant, and therefore, PV, the product, should be a constant. Now, you can see a dotted line drawn here. In this case, you can see the product of PV is a constant for, you can take any pressure value, and for all these pressure values, the value of PV is a constant, and this represents the behavior of ideal gas. Now, these gases, that is you are having nitrogen, carbon dioxide and two other gases, that is hydrogen and helium. For these gases, none of these remain constant. You can see that as pressure changes, there is a change in the value of P into V. In first two cases, that is I am considering hydrogen and helium, as the pressure increases, you can see there is a constant increase in the value of PV. product of PV. See, for the helium also the same is the case. So, here we have a particular pressure and here I am having another pressure. You can see when the pressure has increased, the value of PV, see in this case, in both cases it has increased, but in the former one it was having a lower value. Okay. So, when pressure is increasing, the product of PV is also increasing for in the case of hydrogen and helium. So, this is one type of behavior. It keeps on increasing means I can say that when pressure increases, the product of PV is increasing means it is showing a positive deviation because both are increasing. Okay. Now, consider the case of nitrogen and carbon dioxide. These two are a different type. You can see for nitrogen, as pressure increases, formally in the first it keeps on decreasing. See, there is a dip, and then you can see it crosses the ideal gas equation, ideal gas line, and then it keeps on increasing. In the case of carbon dioxide, you can again see the dip is more deep than in the case of nitrogen, that is it keeps on decreasing as pressure increases and then it increases, crosses the ideal gas equation plot and then it keeps on increasing. So, here you can say that they show a negative deviation. Up till this point, in the case of hydrogen and nitrogen, and for carbon dioxide up to this point it shows a negative deviation. Okay, that is they are showing a value lower than that for an ideal gas. Okay, so these are the PVP isotherms for real gases. If real gases were to obey as ideal gas equation, they should not show any deviation of this sort. So, this is one proof showing that real gases deviate from ideal behavior. Now, to explain these deviation, another factor known as compressibility factor has been introduced. We know that compressibility factor Z, we know that PV is equal to nRT for n moles and we are going to take the ratio of PV by nRT, that is PV divided by nRT, and this factor is considered as the compressibility factor Z. Okay. So, the extent of deviation of real gases from ideal behavior is represented by a factor known as compressibility factor, or it is denoted by the letter Z, that is Z is equal to PV by nRT. Now, what is we can do is Z is equal to P into, okay, I am putting RT underneath with V divided by N. Now, here we know that P is the pressure, V is the volume, R is the universal gas constant, and T of course is the temperature in Kelvin scale. Now, what is N? N is number of moles. This is the number of moles of gas. Now, what I have done here is I have put PV by RT and keeping N V by N another factor. V is the volume divided by volume of the gas divided by number of moles of gas. We will get the volume of 1 mole of a gas because this is the total volume of the gas which contains n moles, and dividing V by N will give you volume per mole, or I can call that to be molar volume, which is represented by the term Vm. It is represented by the term Vm. So, substituting that, I can write the equation Z is equal to P into Vm. Vm stands for V by N. Okay. P into Vm divided by RT. So, that is it. Next, let us go for the deviation from Boyle's law. Okay, deviation from Boyle's law and Charles' law both together. First, we are going to see the effect of pressure. First, we will see the effect of pressure. Now, we are again going to plot the compressibility factor Z against pressure. Okay. Now, again when we watch this, you can see the dotted line represents the ideal gas behavior in which Z is equal to PV by R nRT. Is equal to Z. Now, for an ideal gas, we know that PV equals nRT. So, what will happen to the value of Z now? Z should be equal to 1 because PV and nRT are equal. So, they will get cancelled and the answer will be 1. The value of Z is equal to 1 for ideal gas. So, we will have a value and that remains constant for an ideal gas whether you change the pressure or not. Okay. So, here you can see the value 1 and from 1 I have drawn that dotted line which shows the ideal behavior of the gas. So, Z should be equal to 1 at any conditions of pressure. Okay. Now, again if you watch, see in the case of carbon dioxide, nitrogen and oxygen, you can see that all these they show a initial dip. Dip means a decrease first and then they keep on increasing. While in the case of hydrogen and helium, this is hydrogen and helium, you can see that both of them they keep on increasing. See, it keeps on increasing, it does not show a dip. Now, since this is because we assume that is for ideal gas, it is okay that we neglect the volume of the gas, volume occupied by the molecules and no intermolecular attractions. These are the two assumptions we have been taking in the case of an ideal gas. But in the case of real gases, the volume occupied by the molecules and also the intermolecular attractions, they cannot be neglected under all conditions of temperature and pressure. So, this is the deviation they show, that is because they cannot show the value of Z is equal to 1 and you can see that when the pressure is 0 at very low pressures. We know that when the pressure is very low, it almost equal to 0 means it's a very low pressure. The gas molecules will be far apart and in such cases you can neglect the volume as well as we can consider there is no intermolecular force of attraction because they are all very far away from each other. So, you can see that the values almost, the value of Z is almost equal to 1 when the pressure is considered to be 0. Okay. So, that case is okay, but for these three gases, that is nitrogen, oxygen and carbon dioxide, again they show deviation, that is first they decrease and then increases. Okay. What does it show? That is Z represents the compressibility factor and that is how far the gas is compressible. It gives a measure of how far the gas is compressible. Now, you can see that in the case of nitrogen, oxygen and carbon dioxide, for nitrogen it is not that prominent, but still you can say that they are more compressible than ideal gas. They are more compressible than ideal gas and for carbon dioxide it is very prominent, that is highly compressible than ideal gases. When we take the case of hydrogen and helium, you can see that This hydrogen and helium, they are not that compressible like ideal gas. See, because their values are more than that for an ideal gas. Okay. Now, let us see what is the effect of temperature. Here we are taking, this is all for nitrogen gas. The temperatures are given. Again we are going to plot the value of compressibility factor against the pressure at different temperatures. Okay. So, here you can see that this is for the same gas nitrogen, all these represent for nitrogen, and you can see that when the temperature is minus 70 degrees Celsius, you have a very big dip and then it increases. When the temperature is raised from minus 70 to minus 25 degrees Celsius, the dip or the minimum value is higher than that for that lower minus 70 degree Celsius. Again, as the temperature increases, the decrease minimum, the minimum it is showing, it keeps on increasing, and at 50 degrees Celsius, you can see that for up to this range of pressure, that is from I think it is about 100. The value will be approximately equal to 100. Okay, 0 to 100 atmospheres. 0 to 100 atmospheres, the value of Z is equal to 1, and this is the value for ideal gas. Okay. So, as the temperature increases, the negative deviation or the dip decrease in the value of Z. What happens? It keeps on decreasing, and at the value, the temperature T is equal to 50 degrees Celsius, you can see there is a range where nitrogen gas behaves exactly like the ideal gas. The value of Z at this condition is equal to 1. You can see that in this case, the nitrogen gas behaves ideally at the pressure range 0 to 100 atmosphere. Okay. And the temperature is 50 degree Celsius. Now, this temperature at which the nitrogen gas behaves ideally for a pressure range 0 to 100 atmosphere is known as the boil temperature. Boil temperature means it obeys Boyle's law and also it behaves ideally. That is what it is meant by boil temperature. Now, in this case, this pressure range and this temperature, okay, and we usually focus on the temperature at which the gas can behave ideally, and the temperature is known as boil temperature, which is denoted by the letter capital T with capital B as a subscript. Okay. For every gas, there is a particular temperature for which that gas can obey Boyle's law, Charles' law and Avogadro's law, everything for a certain pressure range, and that temperature for any gas we call it as boil temperature. Now, let us see the difference between boil temperature and the other temperatures for the compressibility factor. There is the compressibility factor Z plotted against pressure, and here the dotted line represents the ideal behavior, or you can say here the value of Z is equal to 1. Now, we are having 3 types of curves, that is when the temperature is less than boil temperature, at boil temperature, as well as when temperature is greater than boil temperature. Now, if you examine these 3 curves, you can see that when the temperature is less than boil temperature, first there is a decrease in the value of Z or compressibility factor crosses the ideal gas equation line and then it keeps on increasing. At boil temperature, you can see there is a certain pressure range at which the gas obeys Boyle's law and shows a ideal behavior in which the compressibility factor Z is equal to 1 for a certain pressure range. When it is above the Boyle temperature, just like what we have seen for hydrogen and helium, it keeps on increasing. There is no dip or a region where it can show the value equals Z is equal to 1. Okay. These are the conditions for a certain gas. And from here we can deduct that we have been seeing the PVP plots, okay, that is for hydrogen and helium. You can see that it keeps on increasing, it is like that. But while nitrogen and carbon dioxide, you saw a dip. This is because in these cases their boil temperatures are in this range and therefore they show a dip. If the temperature is lowered than this temperature, that is it is 0 degree actually. If you go some temperature below that, even hydrogen and helium whose boil temperature is below 0 degree can also show a dip and then go on increasing. Okay. Now, let us move on to the deviation from Avogadro's law. We know that from Avogadro's law, we know that equal volumes of all gases at the same temperature and pressure, if pressure and temperature is kept constant, will have same number of molecules. That is what we have from Avogadro's law. And we have a consequence from that. We have found that 1 mole of any gas occupies a volume of 22.414 liters at STP. Now, what is STP? That is when temperature is equal to 273 Kelvin and pressure is equal to 1 bar, that is standard conditions of temperature and pressure. Now, this is a consequence we have derived from Avogadro's law. So, Avogadro's law states that equal volumes of all gases under the conditions of same temperature and pressure will have same number of molecules, and this is what we have derived from that is 1 mole of any gas, that is mass is fixed, occupies a volume of 22.414. Here temperature and pressure is fixed because it is at standard temperature and pressure. Standard temperature and pressure, temperature is equal to 273 Kelvin and pressure is equal to 1 bar, or sometimes we consider that to be 1 atmosphere, a slight approximation. Okay. Now, if this is so, if all gases they show ideal behavior, and if I am going to take the volume of 1 mole of a gas at STP, I am going to consider it at STP. Okay. At STP, every gas should have the exactly 22.414 liters itself. Now, on experimental determination, it has been found that, see, for hydrogen it is 22.427, the unit is in liters at STP, that is for 1 mole. It is also known as molar volume. The volume of 1 mole means molar volume. Okay. Next is nitrogen, it is 22.405, again that is also different. This is 427, it is a greater value. For nitrogen, you can say it is a lower value than 22.414. Again, when we go for oxygen, it is 22.394, again a lower value. For carbon dioxide, it is 22.264, lower value. Ammonia, it is 22.084, and for chloroethane, this is chloroethane. For chloroethane, it is 21.879. So, these show that the real gases, these are all real gases. These real gases, they do not obey even Avogadro's law. Charles' law does not obey, Boyle's law does not obey, even the Avogadro's law. They do not obey all these three laws. Not always, but under certain conditions they can, but not always, and that shows that all real gases deviate from the ideal behavior. And you can say that the behavior of ideal gas is shown by real gases when the condition is you should have low temperature. Sorry, not low temperature, it is a high temperature, low pressure. Low pressure, and second one is high temperature. In these two conditions, when the pressure is low and the temperature is high, you can see that the gas molecules, they will be occupying a very large volume, or you can say that they expanded form. They get expanded to larger volume. And the assumptions of ideal gas from which the gases show deviations are the 2 points, that is, volume of the molecules are neglected when compared to the volume occupied by the gas. Okay, volume of the molecules neglected. Okay. Second thing is, there is no intermolecular force of attraction between the molecules. These two factors, they are to a certain extent overcome at low pressure and high temperature. When the gas is occupying, it is an expanded form, it is occupying a very large volume. Both the cases, they get rectified, because when gases are far apart and the volume is greater, the volume occupied by the molecules can be neglected. So, that is one condition. And at high temperatures, again the kinetic energy will be more, the molecules will be moving at a higher speed and they will be very far apart, and under these conditions they will not be having any intermolecular forces of attraction. So, these two conditions are helping the gas to behave ideally. So, these are the conditions where gases tend to be ideal. In the other cases, when it deviates, it will deviate from ideal behavior, because all these things, they come into appearance, that is, intermolecular force of attraction should be considered, and also volume of the molecules has to be considered. And this is the reason why the gas has been showing, the real gases have been showing such deviations from ideal gas behavior. To conclude, we have been seeing deviations observed in the plots of PVP isotherms. Isotherms means at constant temperature of real gases. We saw that some of them are showing negative deviations and then positive deviations, some only positive deviation, and these gases, when the temperature is lowered, even those gases like hydrogen and helium which did not show any negative deviation tend to show negative deviations too. Next is the compressibility factor, the value of Z, which is equal to PV by nRT, which should be equal to 1 for ideal gases, is not behaved by real gases, but at Boyle temperature the gases tend to be ideal and they show the value Z is equal to 1 for a certain range of pressure, in a small range of pressure. Only during that pressure, if the pressure is changed, again it is not equal to 1. Next is it shows Boyle's law, deviation from Boyle's law. It shows deviation from Charles' law and also from Avogadro's law. That's all for the session. Thank you.